Okay, welcome back. This is part 3 of the TSSM Physics Trial Exam 2019. This is the last part. We're answering questions 10 to 19 of the written section here. That's the end of the exam. And let's get straight into it. We're starting on question 10. Excuse me. Right. I'm assuming, as always, that you've got the questions with you. And I'm also assuming that you've probably already had a go at this thing. So here's question 10. I'm just going to zoom it in a little bit for you so you can see it on my screen as well. All right. It says Nadia is swinging in a circular arc on a long rope that is tied to a branch of a tree. As he increases the amplitude of his swing, in other words, he goes higher each time, he notices that he starts to feel faint, particularly at the bottom of the swing. His friend Rena notices that his face has started to go pale as his blood is draining away from his head. Explain why this happens while he is swinging. Well, here's the path of the swing. There you go. I'm just going to put the swing in a few different spots. So there's the swing, there's the swing, there's the swing. All right. And as Nadia heads down this way, at any stage in a circular path, you're actually not moving in a circle in an instantaneous fashion. You're moving in that tangential straight line. So everything is trying to go that way, right? And there's a force towards the middle, of course, centripetal force, that keeps pulling you around in a circular path. So when you're there, you're trying to go this way. When you're here, you're trying to go this way. When you're there, you're trying to go this way. Now, your body is on the swing. There you go. Oh, God. Sorry. That was supposed to be a human being. Your body is on the swing. And at the bottom of the swing, your body is trying to go that way, right? But the swing seat is stopping you. That's what's providing the force, and it's drawing you up. However, the blood inside your body can move around a little bit, right? The blood inside your head can still go down that way a little bit, right? It hasn't reached the end of where it can go, right? And the blood here can go down, and the blood here can go down a little bit as well, right? And the blood that's there can travel to there until it hits the seat coming up, right? So in general, anything that can move is going to move away from the middle of the circle, right? This is why when you spin something, if you stir the water inside a bucket, right, the water gets deeper on the edge of the bucket and shallower in the middle, and you create a whirlpool for yourself, right? Things naturally tend to sort of cling to the outside because they're all trying to go through the wall of the bucket. This is what's happening on the swing as well. Okay, so how do you put that into words? Well, excuse me, the way the TSSM actually answered it was pretty good. They put it into words really well. But it's a couple of sentences. You need to say that the motion, when in circular motion, everything is trying to travel at a tangent to the circle, right? But the centripetal force keeps pulling you around the circle. That's the first sentence. Second sentence is, because your blood can move within your body, right? It can actually go part of the way out of your brain, right? Or it can actually move towards the outside of the circle within your body to an extent, right? Before it actually gets dragged around the circle. And that means it can move away from your head, making you feel faint. Words to that extent. All right. Question 11. Okay, here's question 11. I'm going to use the example, the exact paper here as well, because the diagram is important on this one. Okay, use Biro. Figure 6 shows an earthquake shock wave moving from east to west. Note with interest that they've got east and west round the wrong way. Right? That's west, that's east. I don't know why. Anyway, moving from east to west, according to this thing, through a section of the Earth's crust. If the earthquake shock was transverse, along which axis or axes would the Earth move as the shock wave passed through? Okay, a transverse wave looks like this. It's one of those. Right? And as the wave goes that way, which is what they've said, east to west, something that the wave goes through is going to be moved this way. It's going to go up and down, up and down, and up and down. Right? So there are two answers to this question. You've got to get them both to get this right. It's worth 2 marks. Right? So the definition of a transverse wave is that as the wave goes through you, you move, you vibrate, you oscillate in a direction perpendicular to the direction of the wave's motion. But there are two directions that are perpendicular here. Right? The north-south is perpendicular to east-west, and also up and down is perpendicular to east-west. So you have to say both. Okay. So the answer to the question is north-south or north to south or up and down. And the second mark is just for getting the definition of a transverse wave right. You say, well, if the wave is going east to west, transverse waves vibrate things or oscillate things at right angles to that motion. And those two directions are at right angles to the motion. If you got this one right, you're going to get this one right, I think. If the earthquake was longitudinal, along which axis or axes would the earth move as the shockwave passed through it? Explain your answer. All right, longitudinal waves are sound waves. They are those ones that I've shown you with a slinky, where you push the slinky instead of trying to make the slinky do this. You end up just pushing it ahead and you get this pulse that goes along. And the vibration of any particular part of the slinky is in the same direction. Right? I should be doing that down here. As the wave goes past, an item that's in the slinky would vibrate that way and that way as things go past, right? So the answer is, if this longitudinal wave was going east to west, the vibration would be east to west as well, all right? And the explanation of your answer is, yeah, longitudinal waves vibrate things in the same direction as the direction of propagation of the wave. All right, that's 11. Question 12 over the page. Now I'm going to get a diagram here. It says, Carla stretches a string between 2 points 30 centimeters apart, so the speed of the waves along the string is that, 456 meters per second. She then plays notes with the following frequencies on her cello. Now, it's worth noting that string is not on the cello. Right? That's a different string on a different thing in the same room as the cello. Right? I don't think this question makes that particularly obvious. It's not one of the cello strings. Put it this way, if they're 30 centimeters apart, it's a pretty small cello. But this is what's going on. I've got a diagram here. I'm just going to zoom this out a little bit. If I can actually hit, there you go. Okay. This beautifully drawn cello is being struck and sound waves are going through the air, and those sound waves are hitting this string. This is the 30 centimeter string. Right, that light green one, stuck between 2 points, nailed to a board maybe, and it's just sitting there on the wall, 30 centimeters long. And it's been strung tightly enough so that when it is plucked or when it is hit, waves move along it at a speed of 456 meters per second. So that's what's going on. Right? And she doesn't pluck that, she plucks this. Okay. So what's going on with this question? The question is, of the notes played by Carla, which is the lowest frequency that could cause the string to resonate? Excuse me. Okay, here's how you do it. Resonating only happens when you get this string vibrating with a standing wave, and standing waves only happen between two fixed points. I'm just going to draw it down here. There's two fixed points with a string between them. Standing waves are waves where that is a node, that's a node, and there's an antinode in the middle, or there are more than one antinode in the middle, right? So the biggest one, the biggest wave, and therefore the lowest frequency will be this one, right, where the string literally goes like that. Right? The next one, I'm just going to draw a different one, would be if there's an entire wavelength there, because that point and that point will still not have to move because they can't move, right? And there will also be this possibility, 1.5 waves, and the next one is 2 waves, etc. Right. So all of these things will be standing waves. So this one will end up doing this. And this one will end up doing that. I don't have enough fingers. Right? They will look like they're waves that are literally jogging on the spot. And this one will literally go like that, looking like it's jogging on the spot. It won't look like a wave that's traveling from one end of the spring to the other. It will actually be traveling from one end of the string to the other, but it just won't look like that. So these are going to resonate. These are the resonant frequencies. Okay, so let's get back to the maths of this. So it said which one, the question said, of the notes played by Carla, which is the lowest frequency that could cause the string to resonate? Okay, the lowest frequency will be the longest wave. That's the longest wave. That's only half of a wave. The other half is sort of out here. And it's happening on this string. And that's a gap of 30 centimeters. So that wavelength is 60 centimeters. All right, so what do you need to calculate here? We're asked for a frequency, so we need to figure out the frequency of that wave. All right, we know the other things. Frequency is V on lambda, right? V equals F lambda, right? So the frequency of that particular wave is going to be the velocity of it, and they told us in the question it was going 456 meters per second, divided by the length of it, right? And that's not 30 centimeters, it's 60 centimeters. It's the length of the whole wave. And again, it has to be in meters, so it's 0.6. And that comes to 760 hertz. Right? So that's the longest standing wave possible. That's the longest resonant wave possible. And if you look at the question, 760 hertz was one of the notes that was played. There you go. So that's the one. Okay. And that's how you answer it. Now part B says which one of the other frequencies played by Carla could cause the string to resonate. Well, all of these frequencies here, because the wavelengths are getting smaller, the frequencies are going to get bigger, right? The number for the wavelength is getting shorter and shorter and shorter. Lower number, frequency is going to go higher. So you're only going to get higher notes. So if you look at the question again, there are only two numbers that are higher than 760. So forget the other two. It's either going to be 1140 or 1520 or nothing, right? And it has to be a whole multiple of that, right? Because the wavelength of the next one up is just divided by 0.3. And the wavelength of the next one up is just going to be divided by that wavelength. And that's going to be 0.2. And that wavelength is going to be 0.15, etc. Okay, so it ends up being, the math ends up working out that you end up getting a whole number multiple of this. It's going to be 760, or it's going to be 1520, or it's going to be 2180, etc. One of them, two of them, three of them. And that was on the list of the notes that Carla played on her cello. So that's the only other one that's going to work. That's how you do it. Question 13, it says, light with a frequency of 3.3 by 10 to the 15 hertz is shone through a 270 nanometer wide slit. The light is then replaced by light with a frequency of 1.2 by 10 to the 15 hertz. Which frequency will be diffracted more significantly by the slit and why? All right, diffraction happens at its best, is most pronounced, right? Light traveling through a small gap spreads out the most when the wavelength of the light, or the wavelength of any waveform, is roughly the same size as the width of the slit, or the same size as the gap between two slits in a double slit experiment. All right, if this and this are about the same, the diffraction is maximum. Right? In some of these cases, in a question like this, one of the wavelengths is clearly the right size, and the other one's 1,000 times bigger. But unfortunately, these two are both pretty much the same. They're in the same factor of 10. They're both 10 by 10 to the power of 15, and one of them's 3.3, one of them's 1.2. So you're just going to have to do the maths on this one. So you find the wavelengths. You use this, right? Again, V equals F lambda, juggle it around, lambda equals V on F. These are light waves, excuse me. So V is 3 by 10 to the 8, and the frequency they gave it to you, and you just find out what the wavelength is and compare it to the 270 nanometer wide slit. Okay, and again, 270 nanometers is 2.7 by 10 to the minus 7 meters. It's 270 by 10 to the minus 9. That's nano. Okay, 10 to the minus 9. Get the units right. And you find out that one of those things has a frequency pretty much exactly the same. I think it came out to 2.9, so that's the one that will diffract the most. So in your answer, you do that twice, show the two frequencies. One of them is one of them comes to 2.9. The other one, where are we? Sorry, one of them comes to 2.5, pardon me. And the other one came to 9.1, right, by 10 to the minus 9. Sorry, by 10 to the minus 7. So the 2.5 is very close to the same size, so that would diffract more. All right, question 14, still on diffraction. It says some X-rays have the same diffraction pattern as some X-rays have the same diffraction pattern as charged particles with a momentum of that 1.66 by 10 to the minus 23. What is the frequency of the X-rays? Okay. Same diffraction pattern means the same momentum and the same wavelength. Okay. So we've got a formula for momentum. The de Broglie wavelength has got momentum in it. All right. Excuse me. So you've got the momentum. That's Planck's constant, 6.63 by 10 to the minus 31. Find out what the wavelength is. Excuse me. Then once you've got the wavelength, do this, swap those two, find out what the frequency is. Reasonably straightforward, that one. So question 14 isn't too much to deal with. Okay, here's question 15. And right off the bat, I'm going to tell you that the answer to 15B that was given in the TSSM solutions is incorrect. I'll show you why in a minute. It was just a simple typo. Now, most of what they did, their reasoning was correct, but again, they got one word wrong, and it was the important word. But we'll get to that in a minute. All right, so here's the situation. Double slit experiment. A waveform is passing through two closely related slits. It says light, okay. Wavelength of 430 nanometers. It's shone through those slits and forms an interference pattern, okay. All of these are bright lights, right? Bright spot, etc. Excuse me. For the bright light at line A, explain why the path difference must be 1720 nanometers. Okay, there. Now the path difference, you'll remember, is the difference between how far it has to go from that slit and how far it has to go from that slit. Sorry. So, just reminding you of this again. The path difference there at the middle central bright is nothing, because if you sort of draw a straight line there and a straight line there, that blue thing that I've just drawn is an isosceles triangle, right? Those will be the same, which means that as two peaks or two troughs come out through here, they are going to hit that at the same time, and so they're going to hit in phase. So peaks will be together and troughs will be together, and that's constructive interference. That's why you get a bright light. It also happens if the difference between the journeys is a whole number of wavelengths, right? So the first one out, the difference between the two paths is 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths. Same on the other side, 1, 2, 3, 4 wavelengths, right? As long as it's a whole number of wavelengths difference, you're still going to get a peak and a peak hitting at the same time over here, right? And a trough and a trough. So it's still going to be constructive interference, and you're going to get bright bands. In between them, these, I'm just going to mark it in a different color. These spots here that I'm drawing now are where the path difference is something and a half wavelengths, right? It's half a wavelength, 1.5, 2.5, 3.5, right? Which means a peak from one of these slits, is hitting along with a trough from the other one. And they add up to nothing, right? A peak and a trough cancel each other out, so you get a dark spot. You get absolutely no light whatsoever. You've seen me doing it with that laser and the double slit experiment that we did for an assessment 2 months ago. So you know that this is how it happens. All right, so let's get back to the question. For the bright line at A, explain why the path difference must be 1720 nanometers. Okay, the light has a wavelength of 430 nanometers. And we just said this bright light will be a path difference of 1 wavelength, 2, 3, and 4. Right? 4 times 430 is 1720. So they're the two sentences you have to say. Right? You need to say that each bright spot is a spot where there's constructive interference. In other words, the path difference is either nothing or it's a whole number of wavelengths. Right? And being 4 spots out from the central bright, this will be 4 wavelengths. And then you just say 4 of those wavelengths is that. Pretty easy, joining the dots. All right, part B. So here it is. I'm going to get another diagram for you in a second. The wavelength of light is increased and the interference pattern is shifted. The distance L was kept the same. So that's the distance between the slits and the projected wall. That's L there. Oops, sorry. That's L there. Okay. So the distance L was kept the same, but a change was made to the slit separation, which restored the bright lights to their original positions. What change was made to the slit separation? Explain your answer. Okay, I'm just going to get a bigger one of these so that we can play with it a little. Here's one I prepared earlier. Let me zoom it out. Okay. Zoom it out, straighten it up, make it look professional. Okay. So here's the deal. This is 15b. This is about C. We'll worry about that in a minute. Here's the relevant formula. Delta X equals lambda L on D, right? Delta X is the distance between adjacent bright spots, right? Lambda is the wavelength, L is the distance between the slits and the projection wall, and D is how far apart the slits are. All right, so this is a bit of a two-part question, 15b. It said the wavelength of light was increased and the interference pattern shifted, right? If that number gets bigger and everything else stays the same, that's going to get bigger, right? If that stays the same, this is going to be bigger, that'll get bigger. So they would have gone further apart. So this whole thing would have been spread out a little bit, right? Excuse me. And they said that they did not change the L, but they did change something else, and that got these spread apart dots back where they started. The only way to get that number back where they started, if this number is bigger, is to make that number bigger by the same factor. Right? That's grade 8 maths. So that's all you have to say. Okay? They increased lambda and that increased delta X. So to undo that change, they had to increase D by the same factor. Their answer is incorrect because they said decrease instead of increase. Everything else they said was right, but the one word that had to be the right word was wrong, unfortunately, so they gave it wrong. It's very worth looking up the FET simulation of this. We've used it in class before, quite a while ago when we were doing this. It's worth having a play around with this again. And if you actually work this problem, if you actually make these changes, make that change and then make that change, you'll see that to undo that change, you have to increase D. All right, it's worth playing around with that. Okay, 15C, excuse me. If I can get it in front of me, sorry. I've got the wrong sheet here. Right, 15C, it says, consider a point P halfway between G and H. Here we go, there's P. Halfway between G and H. The path difference from the two slits to this point is now 1.275 by 10 to the minus 6 meters. What is the wavelength of light that is now being used? Okay. Again, this is pretty straightforward. The path difference is 0 there. It's 1 wavelength, 2 wavelengths, 3 wavelengths, right, for the constructive interference spots, the bright spots. So the path difference there is 2.5 times whatever the wavelength is. Okay. In other words, the green light, or the wave of light that came from this dot, the green one, traveled 2.5 times the wavelength further to get to P than the blue one did. All right, which means they got destructive interference because it's exactly half a wavelength difference, a crest hit with a trough, you got no light. All right. So given that they gave us what 2.5 of those is, they said the path difference was 1.275 by 10 to the minus 6. And they said, what's the wavelength? Well, divide it by 2.5, and that's the wavelength. Okay? So in your answer, you have to firstly explain how you know that it's 2.5 wavelengths path difference, and then just do the simple maths. All right. Reasonably easy 3 marks. Okay, that's question 5. Sorry, that's question 15. 4 to go. Question 16. It's giving you a diagram there. I'm just going to show it to you. There it is. Figure 8 shows light coming from medium 1 with a refractive index of 1.81 into medium 2. Right. Showed that the refractive index of medium 2 is 1.33. This is a pretty easy one. I just want to show you one thing that people can, that VCE can trick you with. These are the right angles to use. Right. Every now and then, the VCE will trick you by putting a question in, and they don't give you that angle, they give you this one. Right. That's the angle to the surface. That's not the angle to the normal. Right. The angles that you put in this particular formula, Snell's law, I'm going to show it to you in a minute, have to be the angle between the beams of light and the normal, right? It's not to the surface. Every now and then they try to trick you by giving you that angle instead of this one, and you have to be smart enough to spot that. All right, so they didn't do it this time. Here's Snell's law. So Snell's law is the ratio of the refractive indexes of the second one divided by the first, the second medium divided by the first medium for refractive indexes, equals the ratio of the sine of the first angle over the sine of the second angle, or the velocity of light in the first medium divided by the second medium. So it's basically the ends, the sines, and the velocities, and the ends are upside down with respect to the other two. So those are both 1 on top and 2 on the bottom. That's 2 on top and 1 on the bottom. That's how I remember it. You can remember it, of course, by just sticking it on your cheat sheet. All right. But the only way they can trick you with this, again, is they can give you the wrong units, or they can give you the wrong angle. Right. So just be aware of that. But for this question, it's basically just plug the numbers in the way you go. All right. So it's going this way. That's medium 1. This is medium 2. They even labeled them for you in this particular case, so this can't be much easier. All right. So that's 2. That's theta 2. That's theta 1. That's medium 1. That's N1. You're finding N2. Piece of cake. All right. And they even gave you the answer. So you just have to prove to them that doing that formula gets that answer, 1.33. That's about as easy as a Year 12 physics question gets. Finding the critical angle, which is what Part B says, the critical angle is the angle here at which this angle ends up being 90 degrees, in other words, if this beam of light didn't come in at this angle, but it came in maybe here and hit the surface, this would bend a little bit further. Eventually, there is an angle of approach where the angle of refraction is 90 degrees, and it just goes along the surface. It doesn't go into medium 2. All right. So let's, oh God, sorry, that should have been straight. So it's that angle that you're trying to find if that was not a crooked line. That's called the critical angle. So all you have to do is the same thing again. You're going to use Snell's law again. However, that's now 90 degrees, right? So theta 2 is 90, and you're solving it for theta 1, and you've got both refractive indexes. That's why they gave you the answer to Part 1, because if you got Part 1 wrong, you were destined to get Part 2 wrong. Okay. Now, 17 is interesting. I want to have a little chat with you about question 17. So I'm going to get it in front of me. This is a doozy. There's a lot to unpack here. It is actually a very easy 6 marks, but it's also easy to get it way wrong. Okay. In a photoelectric experiment, Lisa shone light beams of varying frequencies. There you go. On a metal plate and recorded the stopping voltages for the photoelectric current for each frequency. She recorded the data in this table, stopping voltage in volts. All right. Lisa used the stopping voltages to calculate the maximum kinetic energies of the photoelectrons in joules for each frequency and then displayed her results on a graph. So she's going to come up with that standard graph that ends up looking like this. This one down here. She's going to come up with this one, right? Where the gradient of that is Planck's constant. And if you come down here, you get the work function, right? And that's the threshold frequency. That's kinetic energy, right? You've seen that 100 times before. She's making this graph, right? But she's done it experimentally, and she has used that voltmeter. All right. So over the page, it says, if Lisa, sorry, I'm just straightening it up for you. If Lisa used the voltmeter shown in figure 9 to record the stopping voltages, what would be the extremes of the vertical error bars for the point with a frequency of 9 by 10 to the 14 hertz? So as she's plotting her points, each of the points she plots has an error, and she's going to draw vertical error bars. And one of these points is for 9 by 10 to the 14 hertz, and that's the frequency, 9 by 10 to the 14. So we need to find out what the kinetic energy is going to be and also what the error is going to be, so we can find out what that spot and that spot are going to be. So that's the question. So this is a lot to do, but it's all pretty easy steps. Okay, so that's how the question is arranged. This is how the answer should be arranged. I'm just going to zoom this in a little bit. Just hold on a minute. That'll do. Okay. There is a moaning cat in the background. I apologize for this in advance. He's having a bad night. All right. So there's a lot to do. It's all pretty easy, but there's a lot to do. And this one, setting out, is important. I want to have a talk to you about that in a minute, but I'll just firstly get through the answer. Okay. The uncertainty in that voltmeter, if you have a look at the picture of the thing, is half the least count. The uncertainty in any measuring instrument, in any measuring implement, like a ruler or a scale or whatever, is half of the least count. Now, the least count is the most accurate gradation, right? The smallest gradation. So there's 1, 2, 3, 4, 5. However, there's these little sort of tick marks between them, right? And there are 4 between the 1 and the 2, so they obviously stand for 1.2, 1.4, 1.6, 1.8. So the least count, the smallest gradation on this thing, is 0.2 volts. So the error inherent in that, just because you chose to use that and because of how accurate the scale is plus or minus half of that least count, which is plus or minus 0.1 volts. Right? So that means the uncertainty in the maximum kinetic energy is going to be plus or minus 0.1 electron volts. Now, the question said she's going to do this in joules. They did say joules there. Right? They're going to display her results on a graph of maximum kinetic energy in joules versus frequency in hertz. That's important. A lot of people are going to miss that one, and they're going to miss this. So the error is plus or minus 1.6 by 10 to the minus 20 joules, right? Because 1 electron volt is 1.6 by 10 to the minus 19 joules. So it's just applied the conversion factor. So that is the size of the error. So that, getting back to this little graph here, sorry, that I drew, that is how far up and how far down we're going to make the error bars go from the point. All right. So we're sort of halfway there. So now we get to this bit here. So the question said, once again, I'm just going to remind you of what the hell we're doing, because this has got a lot of steps. Right? The question said, find the error bar extremes. So we're finding that spot and that spot, right? For the point corresponding to a frequency of 9 by 10 to the 14 hertz. Okay, so for this point, you have to go back to her table. Here's the table. There is 9 by 10 to the 14 hertz, right? Light frequency times 10 to the 14, there's 9. Stopping voltage, 1.73, so that's what we're using. Don't need this anymore. So the stopping voltage in electron volts is going to be, or the energy, pardon me, in electron volts is going to be 1.73, right? Converting that to joules, right, multiply it by 1.6 by 10 to the minus 19, it equals 2.77 by 10 to the minus 19 joules. So that is the value of the point itself. That's going to be 2.77 by 10 to the minus 19. The question said, well, don't worry about what that is. Where is that? And where is that? So these are the two answers we need to give. So that's the value of the point. This is the error, plus or minus that, and we just have to plus that and get the answer, and then minus that and get the answer. And that's what I've done down here. Error bar extremes, this figure plus 1.6 by 10 to the minus 20, that's the answer. And this figure minus 1.6 by 10 to the minus 20, that's the answer. It's a lot of little stuff to do, right? That's why it's worth 6 marks. There's plenty to get through here. But what I want to emphasize here is the setting out. One of the reasons I've left this for about a week of the holidays is hopefully you've done this practice exam quite a few days ago. I want you to look at how you set out this question. Did you say that? Or did you just go from here to here, right? Did you have these little sort of headings here? Did you tell the person who's marking the exam what on earth you're doing, right? Did your answer start generally at the top and work its way down? Or did it start at the left and work its way right? Or is it all over the place, right? This really does matter. In a big question like this with lots of steps, it's important to communicate well. This is a 6 out of 6 answer, but it could have been a 3 out of 6 answer if it was higgledy-piggledy. I could have had the same figures, the same answer here, and the working could have been so bad that nobody was going to find more than 3 or 4 marks, right? Set your stuff out well, right? Do what your math teachers have been telling you for 6 years, right? Setting out matters, right? And this is a classic case where the setting out is potentially going to either win it or lose it for you by quite a bit, because that's a big question. 6 marks, and it's a reasonably easy question if you just know these few facts. Right. All right, here's question 18. In the photoelectric experiments at the start of the 20th century, about 120 years ago, the energy of photoelectrons was found to be dependent on the frequency of the light that was causing it, right? The higher the frequency of light that was shone on the metal, the higher the energy of the electrons that came out of the metal had. All right. Explain why these findings were a challenge to the wave model of light. The answer to this is that the wave model of light gave you the idea that the intensity of the light would give you more energy. It made complete sense. It takes more energy to make a more intense light. You have to put more watts through it or get another light bulb, and you have to use more electricity. Excuse me. So it made complete sense that a more intense light with the same frequency should have given you more energetic electrons, but that didn't happen. So that's the answer. All right. The wave model predicted that a more intense light would give more energy to the electrons, and that didn't happen. All right. How did Einstein explain these findings in terms of the particle model of light? Now, this requires a little bit of detail here, and I'm going to show you how to answer this one really well. Okay. I'll zoom out, sorry. Right. This is worth 4 marks, and here are where the 4 marks come from. There are 2 parts to this because there are 2 observations that had to be explained. The 2 observations were that more intense light didn't give photoelectrons any more energy, and that higher frequencies did give them more energy. So Einstein tried to explain both of those things, and here is how to do it. You don't even have to put these in this order, right? But this is the way I did it. Okay, so Einstein said the light was quantized into particle-like bundles called photons. They're not particles, they're particle-ish. They don't have any mass, they're not particles, but they act like particles, right? In that they are discrete little bundles. They're not a continuous wave like we tend to draw them, right? And their energy, the energy of every one of these, was only dependent on their frequency. And that theory explains this observation, right? Therefore, higher frequencies would give you higher energy, for the electrons to absorb. Right? A higher frequency would make more energetic photons. When they hit the electrons, you end up getting more energetic electrons. That observation was explained by this theory. Okay, and the other observation was about the intensity. More intense light equals more photons, but each photon still has the same amount of energy that it had before. There are just more of them, right? There's no more energy per photon, right? So they're not more energetic photons. So when one of these photons hits an electron, it still gives that electron the same amount of energy. Therefore, more intense light gives you more photoelectrons. There's a higher photocurrent, but they're going to have the same amount of energy. Once again, that observation was explained by this theory. That's why it's worth 4 marks, this one, right? There were 2 observations that were handled by 2 bits of theory. That's the things that this answer is looking for. You can put them the other way around. You can go green, then black, right? But those are the 4 things that got you the 4 marks. Question 19, final question. You've made it to the end. Congratulations. All right. Figure 10 shows the atomic energy level diagrams for sodium, mercury, and hydrogen. And again, I've said this a lot, but when you're given a graph, when you're given a diagram, just forget that for a minute. Right? Don't worry about the question, just look at the thing. Take 10 or 15 seconds and just understand it. Right? For example, a few things about this one. The energy is in electron volts, it's not in joules. So if we have to use Planck's constant, we're going to use the 4.14, the one that's for electron volts. Right? Worth noting. Sodium, mercury, and hydrogen are down here, so that's sodium, that's mercury, that's hydrogen, and it's also worth noting that sodium has the 0 down here and goes up to 5.1, and these other guys have the 0 at the top and goes down. This is nothing particularly to worry about, right? Where the 0 goes is totally arbitrary, but this is ground state down here, right? So these are the amounts of energy that it takes to get an electron from the ground state of sodium, from the 1s orbital, up to, not the 1s orbital, sorry, the lowest, the ground state orbital for the first electron that's going to move, right? Up to different orbitals that are normally empty. And the last one is how much energy it takes to get something from one electron, from the ground state out of it. In other words, to ionize the atom, right? So it's arbitrary that you call that one 0 and you go up in energy. You can also call just being released from the electron, from the atom, 0 and go down in energy there, right? It's totally arbitrary, isn't it? It really doesn't make much difference. What's important here is the gaps, the energy gaps between these different levels, right? If that's a 5.5 and that's a 10.4, the difference between those is 4.9. So it takes 4.9 electrons for an electron, 4.9 electron volts for an electron to jump from there to there. And when it jumps back down, it's going to release a photon that's got 4.9 electron volts worth of energy. That's the important thing, okay? But it's just worth stopping and just taking 15, 20 seconds to look at it and understand what you're seeing. Okay, now let's get to the question. 3 students, Raina, Alyssa, and Carl, were analysing absorption spectrums obtained from a sample of hot gas to see if sodium, mercury, and hydrogen were present in the sample. They found that there were 2 clear absorption lines with wavelengths of 185.4 nanometers and 496.8 nanometers. Part A says, show that the energies in electron volts of the absorbed wavelengths were 2.5 electron volts and 6.7 electron volts. Now, there was a typo in the answer. I'm just going to ditch this for a minute. If you have a look at the TSSM answers, this is what the formula should have said. Right? This is what you're going to use. You use E equals HF, but you get rid of F and replace that with C on lambda. Right? E equals HC on lambda. The TSSM solutions wrote it like this, HC on gamma, right? And that's the Lorentz factor thing. So just a regular typo, but they didn't mean that. They meant this. Okay. So Planck's constant, again, 4.14 by 10 to the minus 15, because we're dealing with electron volts here. Speed of light, wavelength they gave you, find the energy. All right. So you do that for each of them. Excuse me. So you do that for each of those and you'll get an answer of 2.5 electron volts and 6.7 electron volts. It'll just show the working. That's reasonably easy. Over the page, sorry, on the next page, still have a whinging cat. I might deal with my whinging cat, just hang on. Okay, I cannot guarantee that I have sufficiently dealt with the cat, but you know, we'll plug on. Last question. Okay, so here's what's going on here. Rayner thought that the lines indicated that only one of these three elements were in the sample. Alyssa thought there were two elements in the sample, and Carl thought all three were in the sample. Which one of them is correct? Clearly explain your answer using the energy level diagrams. This is worth 5 marks. You've got to do 3 things, right? Which one of them was correct? So you have to give a name. Don't forget that bit, right? With these big questions, a lot of people do all the calculations, blah, 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 and they forget to actually answer the question as it was stated, right? You've got to say Rayner was correct, or Alyssa was correct, whichever, right? Clearly explain it. That's the second thing you've got to do. That's probably worth 2 or 3 marks, and use the energy level diagrams to explain it. If you explain it some other way, you can't get full marks. All right, so here's the deal. Those electron jumps were 2.5 electron volts and 6.7 electron volts. What you have to do is look at this and see if there are any jumps of 6.7 electron volts or 2.5 electron volts anywhere along here. So take it one at a time. Sodium, the whole range is only 5.1, so it won't have a jump of 6.7. And if you have a look at it, it doesn't have any jumps of 2.5 either. That's 2.1. 2.1 to 3.2 is 1.1, that's 1.5, right? If you go each number minus another number, you don't get 2.5, you don't get 6.7. So there is no sodium in the mystery gas that they tested, right? As if there was, you would have got one of these other jumps, but they didn't get any of them. Okay, 10.4 minus 3.7 happens to be 6.7, okay? So the energy gap there is 6.7 electron volts. So that's pretty hard evidence that there is some mercury in their sample gas. And 3.4 and 0.9 are 2.5 apart, right? And so that's pretty hard evidence that there is hydrogen present. So that's pretty much all you have to do. You have to state one at a time, right? So you say sodium, there's no gap of 6.7, that's impossible, and there are no gaps of 2.5, so there's probably no sodium. Mercury, you say the difference between negative 3.7 and negative 10.4 is 6.7, therefore there is almost certainly mercury in the sample. Same deal here, 2.5 exists on this, therefore there is almost certainly hydrogen. And the final thing you have to do is you have to say, therefore, Alyssa is right because she said there would be 2 gases. All right. So you need to deal with these things clearly using the figures that they gave you one at a time and then state the answer. Okay, that, my friends, is the end of the TSSM 2019 practice exam. Bye-bye.